Hi everyone. So I'm a grad student and today I wanted to review substitution reactions. So basically I'll talk more about SN1 versus SN2 reactions. People usually study them in high school or sophomore organic chemistry, and there are various textbooks which talk about them. So basically any good organic chemistry textbook will talk about it, and I just prefer Clayden over other books, but you can refer to any textbook you want, any high school or sophomore organic chemistry. But the thing is, sophomore organic chemistry will probably talk more about it in more depth as compared to high school textbook. But anyway, so basically substitution just mean replacement of one thing with another. So it's just an everyday example I took, that suppose you prefer a product of brand X, but then suddenly you decide to not use it anymore but switch to a brand Y. So that's just substitution. And so it's similarly in organic chemistry, we replace one group in a molecule with another. Sorry, excuse me. Yeah. So we replace one group in a molecule with another group. So the example I took here, there's an ROH, and if we make it react with HX or um a halo acid, then the alcohol functional group will get replaced and it will be replaced by halogen, and you will get water as the byproduct. Of course, the it's not the exact reaction conditions, but I wrote it as a generic form, like just as a example. But I'll talk about specific reaction later with exact example. So now, what's SN1 versus SN2? So SN just stands for substitution, and 1 or 2 refers to, I'll talk about it later, but it refers to the type of substitution mechanism. So 1 basically means that the rate equation of that substitution reaction is dependent only on one species, while in SN2 that rate is dependent on two species. Now what those species are and how to determine rate constant, I'll talk about that later. So no, yeah, so I've written here that number indicates the number of species in the rate law equation. And this makes it interesting that SN1 have two steps and SN2 have a single step. So again, what these steps are, I'll talk more about it, but usually someone might think that okay, SN1 should have one step and SN2 should have two steps, but that is not the case. So let's just say that here, so this is an example of SN2 mechanism. So this is oh no, sorry, it's not SN2. So basically this is a substitution reaction where OH is a poor leaving group. It doesn't have any incentive to leave as OH negative, so it doesn't like to do that. So oxygen have two lone pairs, so it just wants to abstract a proton from the acid and become OH2 plus ion or oxonium ion. So this oxonium ion is a good leaving group because it leaves as water molecule. So right here, sorry, yeah. So right here it leaves as water molecule. So right here it just leaves as a water molecule, so it have incentive to leave. OH minus doesn't have a good incentive to leave. So now let's talk about mechanism, and when I talk about mechanism you'll see why it's a 2-degree mechanism. So basically SN2 reactions happen with a backside attack where the incoming nucleophile, so this X minus is also called a nucleophile. It can be any halogen like chloride or bromide. They can be a nucleophile here in these substitution reactions. So these attack our main carbon and the leaving group leave simultaneously in a single step. So the incoming nucleophile comes and the outgoing leaving group leaves. Now what's interesting is that uh, there is inversion in stereochemistry. So what happens is that the group which was on the front side of the molecule now becomes the back side of the molecule, while the back side of the molecule becomes the front side. And we can talk about it in the transition state. So what happens is that in the transition state, the three groups attached to a carbon can be seen here, but the incoming nucleophile and the outgoing leaving group are attached simultaneously at the same time to the leaving group. So they are just there, and this bond will eventually get stronger and this bond will eventually get weaker. And so the rate of that equation can be written as the rate constant K times the concentration of alcohol, initial concentration, times the initial concentration of halide, because in the it's since it's a single step reaction, there's only one step, and for that rate determining step, the rate is dependent upon the species of our initial alcohol and halide at the same time, or the nucleophile at the same time in a single step. So that's why the rate equation is dependent upon both the steps. Then let's talk about the SN1 reaction. So now SN1 reaction happens in two steps, and rate dependent and rate dependent only on one species. So this is just, but then let's talk about the mechanism. So in this, the leaving groups leaves, and there's a formation of a carbocation, which means positive charge on the cation, and this is step 1. Then step 2 is that this carbocation is attacked by the incoming nucleophile, and so in this case the nucleophile is planar. It's explained in Claydon really well, like they have drawn the possible geometric configurations with the molecular orbitals. I have not included them here, but you can read more about the carbocation in Claydon. So the incoming nucleophile have option to attack from any side it wants. So what happens is that you get a racemate, which means that both the stereoisomers are observed, and like both are possible, and usually in ideal case scenario the ratio of them would be 1:1 or 50 and 50. So what it means is that they would be in equal concentration. So basically they racemate, yeah. So it's just 1:1 ratio. So that's what I've written, that it can attack from both the backside and the front side. So in case of a backside attack, there's inversion of stereochemistry, but in case of front side, there is retention. And since both of them are 50-50, they negate the effect of each other, and in the end, you get a racemate. Yeah, so since both of them are equally likely, there are certain ways when you can make one more likely over other, but in general, in a normal SN1 reaction, they are equally likely. And so to write the rate equation, we look at the slowest step, which is also the rate determining step. So in the slowest rate determining step, so this is the rate determining step, and in this step there's no nucleophile involved, just the initial alcohol and the leaving group leaves. But in reactants there is only one reactant which on which the rate is dependent for the entire mechanism. So in this lowest step there's only one species, and so the rate constant, or so the rate would be equal to rate constant times the concentration of alcohol, that's the initial concentration. So that's why it's SN1, because the substitution is dependent only on the concentration of one species when it comes to the rate. So now it's just a quick table to compare between SN1 versus SN2. So SN1 is a two-step mechanism over SN2, which is just one step, and I've already explained it. Now, interesting thing is that for SN1, 3 degrees, so basically 3 degree means that the central carbon atom is attached to three other carbon atoms. 2 degree means that central carbon atom is attached to two carbon atoms. 1 degree is just one other carbon atom, and so 0 degrees that our carbon atom we are interested in have three hydrogen atoms and there's no leaving group involved. So 3 degree is more likely to undergo SN1 over SN2, and that's because carbocation is stabilized by inductive effect. So what it means is that methyl groups or ethyl groups are basically our electron donating group. So they have negative charge, partial negative charge I should say, or sorry, inductive effect doesn't have any charges, but methyl group tends to donate its electron density to the central carbon atom slightly, and so it donates some electron density through inductive effect. There's no charges involved, but it's just some transfer of electron density. So the carbocation is stabilized, and 3 degree is preferred, and that's because it's the slowest step. And 3 degree carbocation, since when the carbocation is more stable, this reaction is pushed in the forward direction because carbocation stability would be preferred. And in SN2, 3 degrees the slowest, and 1 degree or just methyl attached to a living group is the fastest, and that's because in SN2 reactions sterics are involved, because for the backside attack, if these R1, R2 and R3 are bulky groups, then the nucleophile won't be able to attack the central carbon atom, and the reaction would not be able to take place effectively. But if they are methyl groups or just hydrogen groups, or like very light groups like two hydrogens of one methyl, so effectively the nucleophile would not have any hard time attacking our carbon center. So again, that's what I've written, because if steric more hindered makes it difficult for nucleophile to attack. Then in SN1, since carbocations are involved, rearrangements are possible, because the nucleophilic attack is the second step. But if a carbocation sees that it have opportunity to make even more stable carbocation using resonance, then it can do so. And in case of SN2 reaction, rearrangement is not possible because it's a single step reaction and there's no carbocation formation, so there's no scope for rearrangement. So thank you, that's all for today.